Kia ora, no Aotearoa. The other day I came across an incredible comedy channel called Brian's Logic. The video I watched was him explaining how GPS does, or rather doesn't, work. For over half an hour. It was hilarious. It reminded me of some of the Monty Python sketches where they would talk utter nonsense with a straight face. Well, Brian certainly had that down pat, talking about angles, triangles and trigonometry like he knew what he was talking about. All with a serious sounding voice. It had me in stitches. After my wife picked me up off the floor and gave me a paper bag to breathe in, I decided to make myself a pickup to calm me down. So I mixed 4 shots of espresso with 4 shots of whiskey and sat down to enjoy my medicinal compound. Brian was still going.
You don't know at what angle there would be between the tangent and the chord, and the hypotenuse here and the chord. You can't figure that out because you don't know what arc there is. You don't know what length of arc. You can't do any of that. There's no way out. It's over. I'm sorry. Now I'm going to leave it at that because I don't think I shouldn't really need to go any further. That should really have cemented it. I don't see why after that you can have any questions for me. The questions should be for the people telling you that this is how GPS works when it's not, because it can't. End of story. Thanks for watching.
You see? Utter nonsense. I know that GPS works. I use it all the time, and it hasn't failed me yet. Before I went to subscribe and like the video, I decided to take a look at the comments to see what others thought of it. To my surprise, there were hundreds of comments telling Brian that he was wrong. Surely these were not viewers who didn't get the joke. It had me wondering whether I had the wrong end of the stick. So I decided to watch a few of Brian's other videos. Oh dear. I was wrong. Brian really does believe all the nonsense he spouts. So I decided to try and show Brian and any other flerfs who might agree with him how GPS actually works. Now, I'm not an expert, but I do believe that I have an understanding of the basic. There's one thing I learned over 50 years ago, and that's the KISS principle. Keep it super simple. Since GPS works with moving satellites in 3 dimensions, there is quite a bit of maths involved. So to simplify this and keep the maths to a minimum, I decided to explain the principles in 1 dimension with stationary transmitters. Let's take a 1-dimensional track along which I'll be hiking. Since it's 1-dimensional, it's straight and level. I start my hike at one end of the track, and let's call that A, and travel along the track aiming to finish at the other end, which I'll call B. I know that the track is exactly 10 kilometers long. In order to assist hikers on their walk keep track of the distance they've traveled, 2 explosions will be detonated every 15 minutes, one at point A and the other at point B. These explosions are detonated at exactly the same time and exactly on the hour and every 15 minutes in between. The explosions I'll be using here are the ones that occur at 12 noon. On the day of my hike, the conditions are such that the speed of sound is 1/3 of a kilometer per second, which means that for every 3 seconds, it travels 1 kilometer. When my watch alerted me that the time approached 12 o'clock, I stopped to measure the time that the explosions reached my ears. I'll call this point C. Now let's call the distance between the start of the track and my current location X, and the distance between my location and the end of the track Y. I heard the explosion from A at 14 seconds past 12. And the explosion from point B at 26 seconds past 12. I realized that my watch wasn't showing the exact time, so I need to use both of these times to determine how far along the track I was. The difference between 26 and 14 seconds is 12 seconds. Since sound travels at 1 kilometer every 3 seconds, this equates to 12 divided by 3, or 4 kilometers. Now, since the second explosion came from B, the distance y is larger than distance x. To calculate where I was, I first note that since the track is 10 kilometers long, the distance traveled plus the distance to the end of the track must be 10 kilometers, or y plus x equals 10. I know that the difference between my location and the start, and the distance between my location and the end, is 4 kilometers. So y minus x equals 4. Now, if I take the difference between these two equations, or subtract one from the other, I get y minus y equals 0. Now, subtracting a negative number is the same as adding a positive number, since two negatives make a positive. So x minus negative x is the same as x plus positive x, or plus 2x. 10 minus 4 equals 6. So 2x equals 6. Dividing both sides by 2 results in x equals 3. So I'm 3 kilometers from the start of the track. So now I know my location. But the calculations of the information I've gained from these explosions give me one more useful fact. I know that the distance from A to C is 3 kilometers. The speed of sound is 1/3 of a kilometer per second, which equates to 1 kilometer every 3 seconds, and that the explosion took place at exactly 12 o'clock. So I actually heard the explosion from A at exactly 3 kilometers times 3 seconds per kilometer, or at 9 seconds after 12. Yet on my watch, the time was 14 seconds after 12. So I now know that my watch was 5 seconds fast. Now that's basically how GPS works. Before I take a look at 2 and 3 dimensions, however, let's bring our one-dimensional example into the 21st century. I'll call this the TPS, or Track Positioning System. I'll start with the same 10-kilometer track, marked with A and B for start and finish. Instead of explosions, we now have a clock and a radio transmitter at each end, each sending its location and time once every second. Since we're dealing with a radio signal and not sound, we need to know the speed of light instead of the speed of sound. This is known as C, and is 299,792,458 meters per second, which is approximately 3.3 microseconds for every kilometer. Instead of a watch, I now need to carry a radio receiver and a computer. When I'm ready to check my location, I'll stop and call this point C. And as before, the distances from A and B I'll call X and Y. My computer takes a reading from the radio signal and determines that the difference between X and Y is 9.9 microseconds. If we divide this by the speed of sound, we get a distance of 3 kilometers. Using the same method as before, I subtract the difference of X and Y from the sum of these two, resulting in 2x equals 7 or x equals 3.5 kilometers. If we take this to 2 dimensions, we'll need 3 transmitters. Once we know the transmitters' locations and times, we can calculate our distance to each of these transmitters and find our position in 2 dimensions. For example, if we are 1036 meters from transmitter A, we could be anywhere on the circumference of the circle with a radius of 1036 meters centered on A. If we add a second result, the distance from transmitter B of 769.5 meters, our location is narrowed down to 2 possible locations. With the third result of 314.5 meters from transmitter C, we narrow our location down to just 1 spot. Now, in the real world, we need to find ourselves in 3 dimensions, which means working out the distance from 4 transmitters. The Navstar GPS system houses these in 31 satellites, of which 27 are in operation at any one time. These satellites are in orbit at a distance of 20,180 kilometers above Earth, and each satellite orbits the Earth twice a day. According to the National Institute of Standards and Technology, each of these satellites has several atomic clocks on board. These clocks keep time very accurately to within 3 nanoseconds or 3 billionths of a second, and are regularly corrected using even more accurate atomic clocks that are kept on the ground. They need to be synchronized because accurate time is the basis of GPS location and navigation services. The GPS satellites are constantly broadcasting signals with their time and position over Earth. The GPS receiver in your mobile device compares the time signals it receives from the satellites with its internal clock. Knowing the speed of light and when the signals were sent and received, your device can calculate your distance from each satellite and thereby home in on your longitude, latitude, and altitude. Hopefully my explanations have shed a little light on Brian's understanding of the subject. And if I have informed or entertained anyone else, please let me know in the comments. If you'd like to know more about GPS, I've listed a few sites in the comments which I recommend. Ka kite anō.